Hey kids, welcome to section 8.3 t-test for mean. Today we're going to learn how to do a hypothesis test for means when sigma is unknown using the t-test. Okay, so when the population standard deviation is unknown, the z-test is not typically used for testing hypotheses involving means. A different test called the t-test is used. The distribution of the variables should be approximately normal. Super important. Always check to see if stuff is normally approximated. There are two assumptions that you need for the t-test for a mean. One, the sample must be a simple random sample. And two, either your sample size is greater than or equal to 30, or if the population is normally distributed, then your sample size can be less than 30. There is a test statistic for the hypothesis test for mean. You are going to do x bar minus mu over s over root n. So you're going to take your sample mean, subtract your population mean, divide by your sample standard deviation over the square root of the sample size. Notice that your degree of freedoms is n minus 1. So when you're looking up on your chi-square table or your t-table, you're going to want to make sure that you subtract 1. Your 5 steps for a successful hypothesis test are listed below. State the hypotheses and identify the claim. Find the critical value from table F and also draw your picture. Compute the test statistic, make a decision to reject or not to reject, and then finally summarize the results. So let's see how we do one of these hypotheses tests. A medical investigation claims that the average number of infections per week at a hospital in southwestern Pennsylvania is 16.3. A random sample of 10 weeks had a mean number of 17.7 infections. The sample standard deviation is 1.8. Is there enough evidence to reject the investigator's claim at alpha equals 0.05? Assume the variable is normally distributed. That's important because our sample size is less than 30, so we need to make sure that it comes from a normally distributed population. All right, let's take a look at what our numbers are and what the variables are. So 16.3 is our population mean, so that's our mu. 10 weeks is our sample size, that's n. And don't forget, we need degree of freedom is 9. We've got a mean number of 17.7, that's our sample mean. And we also have a sample standard deviation, that's our S, is 1.8. So now let's write our hypotheses. The medical investigation was claiming that it was 16.3, so that's our null hypothesis, mu equals 16.3. It's also our claim. Now, it doesn't say anything about the problem about being greater or less, so our alternative hypothesis is not equal to. So we're going to draw our picture. It's not equal to, so we're going to shade both ends. We're going to take our alpha of 0.05 and we're going to split it into 2. So 0.025 is in each of the shaded areas. Our critical value is t. We have a positive and a negative. To find the actual critical value, we're going to go to our t-table. We have 9 degrees of freedom, and we have 0.025 in one tail or 0.05 in both tails. That gives us a test or a critical value of 2.262. All right, so now we're going to do our test statistic. So the formula for the test statistic is t equals x bar minus mu over s over root n. So we're going to take 17.7, subtract 16.3, divided by 1.8 over the square root of 10. Now, since our critical value had 3 decimals, our test statistic has 3 decimals, and we get 2.460. All right, so now we have to see if we reject or fail to reject. Our cutoff critical value is 2.2. 6.2, we have a test statistic of 2.4. That means it's in the critical region, so we are going to reject the null. So we're going to say since 2.460 is in the critical region, we reject the null. All right, since we reject the null hypothesis and the null is our claim, then there is enough evidence to reject the claim. There is enough evidence to reject the claim that, and so reject the claim that the average number of infections is 16.3, that the mean number of infections is 16.3. We can answer the question, is there enough evidence to reject the claim? And the answer is yes. Okay, let's take a look at a next one. This one has to do with starting salaries for nurse practitioners. According to payscale.com, the average starting salary for a nurse practitioner is $79,500. A researcher wishes to test the claim that the starting salary is less than $79,500. A random sample of 8 starting nurse practitioners is selected and their starting salaries in dollars are shown. Is there enough evidence to support the researcher's claim at alpha equals 0.10? Assume the variable is normally distributed. Okay, so in order to do this problem, I need to know what my mu is, what my x bar is. I need to know my sample size n, my degrees of freedom, and my sample standard deviation. Okay, so they give us mu is 79,500. They also give us that n is 8, which means our degree of freedom is 7. And that's kind of all they give us. So we're going to have to use the calculator to figure out what the x bar is, and we're going to have to use the calculator to figure out what the sample standard deviation is. So if you put those into your calculator using 1var stat, you'll be able to find that the sample mean is 75,150. And that your sample standard deviation is 6,937.7. Notice that I rounded my standard deviation with 1 decimal because my data had no decimals. All right, now let's come up with our hypotheses. Our null hypothesis is going to be mu equals 79,500. My alternative hypothesis is mu is less than 79,500. And the alternative is my claim. We can draw a picture. We are less than, so we're shading to the left. We keep our alpha at 0.10. Now we need to find our critical value. Because it's on the left-hand side, it's negative. So we have 7. Let's get rid of this. So we have 7 degrees of freedom and 0.10 in one tail. 7 degrees of freedom, 0.10 in one tail gives me 1.415. So I'm going to make that negative 1.415. All right, now let's find our critical value. X bar minus mu over S over root n. X bar is 75,150. Our mu is 79,500. Divided by our sample standard deviation, 6,937.7 over the square root of 8. If I plug this all into my calculator and round to 3 decimals, like my critical value, I get negative 1.773. So let's decide if it's in the critical region or not. So if my cutoff is negative 1.415 and my test statistic is negative 1.7, that puts me in the critical region. So we're going to reject the null. So since negative 1.773 is in the critical region, we reject the null hypothesis. And since we reject the null and the alternative is our claim, there is enough evidence to support the claim. There is enough evidence to support the claim. And our claim was that the starting salary is less than $79,500. That the mean salary is less than 79,500. So our question, is there enough evidence to support the claim? And the answer is yes. All right, let's go on to the next slide. This time we're going to be talking about joggers' oxygen intake, something I should probably start doing. All right, a physician claims that joggers' maximal volume oxygen uptake is greater than the average of all adults. A random sample of 15 joggers has a mean of 40.6 milliliters per kilogram and a standard deviation of 6 milliliters per kilogram. If the average of all adults is 36.7 milliliters per kilogram, is there enough evidence to support the physician's claim at alpha equals 0.05? Assume the variable is normally distributed. Okay, well, we need an X bar, we need a mu, an N, a degree of freedom, and an S. So our X bar is the sample mean, which is 40.6. Our population mean, mu, is 36.7. Our degrees of freedom is 15, or our sample size is 15, which means my degree of freedom is 14. My sample standard deviation is 6. So now we have our hypotheses. Our null hypothesis is mu equals 36.7. Our alternative hypothesis is mu, is greater. So we have greater than 36.7, and that is our claim, is the alternative. We draw a picture. We're graphing greater. That's our alpha at 0.05. Okay, so now we need a critical value. It's on the right-hand side, so it's going to be positive. So we need 14 with 0.05. 14 degrees of freedom, 0.05 in one tail. So we're looking at 1.761. Okay, let's calculate our test statistic. T equals X bar minus mu over S over root N. So we have 40.6 minus 36.7 over 6 over root 15. Type this into our calculator, round to 3 decimals, we get 2.517. So let's see, our cutoff is 1.761. Our test statistic is 2.5, so we are definitely in the critical region. So since 2.517 is in the critical region, we are going to reject the null. We reject the hoe. Okay, so since we rejected the null hypothesis and our claim was the alternative, there is enough evidence to support the claim. There is enough evidence to support the claim that, and our claim was that the average was greater than 36.7. The claim that the mean is greater than 36.7, we'll go ahead and throw in milliliters per kilogram. So answer the question, is there enough evidence to support the claim? And the answer is yes. Okay, so the next slide here just kind of gives you an overview of the difference between section 8.2 and section 8.3. 8.2 is when we did a hypothesis test for sigma, or for the mean, but we knew sigma, and so we used a z-test. This was section 8.2. Then we moved on to section 8.3, and that's these two. If sigma is unknown, but n is greater than or equal to 30, you can use the t-test. If sigma is unknown and n is less than 30, we can also use the t-test as long as the population is approximately normally distributed. So again, if you start here, ask yourself, do you know sigma? If you know sigma, boom, go to the left and use the z. If you don't know sigma, go to the right and you're going to use t. So this chart's just there to kind of help you differentiate between when you know sigma and when you do not. All right, here is an application. How much nicotine is in those cigarettes? A tobacco company claims that its best-selling cigarettes contain at most 40 milligrams of nicotine. This claim is tested at the 1% significance level by using the results of 15 randomly selected cigarettes. The mean is 42.6 milligrams and the standard deviation is 3.7 milligrams. Evidence suggests that nicotine is normally distributed. Information from a computer output of the hypothesis test is listed. So we have a sample mean, that's our X bar. We have a sample standard deviation, that's our S. We have a sample size 15, which is N. Degree of freedom is 14. We have a p-value. We don't really use p-values much, but that is part of a different kind of hypothesis test. We have a significance level. That's our alpha. We have a test statistic. That's the one that we get from the equation. And we have a critical value. That's the one that we get from the picture. So what are the degrees of freedom? Number one, the degrees of freedom are 14. Is this a z-test or a t-test? Well, notice that you have test statistics and critical values with t, so this is a t-test. You also know it's a t-test because you have the sample standard deviation, not the population standard deviation. Is this a comparison of one or two samples? We have only chosen one, so this is a one sample test. Is this a right-tailed, left-tailed, or two-tailed test? Well, in order to do that, we probably need to come up with what our hypotheses are and then draw a picture. So our null hypothesis, if we look back, our null hypothesis was at or 40. So we're trying to say at most 40. So this is where it gets a little weird. If your null is mu equals 40, here in the alternative hypothesis, you're only allowed to put a greater than, a less than, or a not equal to. But our problem says at most. Now, at most means less than or equal to. But unfortunately, I can't put less than or equal to into the alternative hypothesis because I'm not allowed to have an equality sign. So therefore, we're going to take everything that's not less than or equal to, or everything that is greater. So we're going to put greater than 40, and that's our claim. Now, since it's greater than 40, we're going to be shading on the right. That means this is a right-tailed test. By comparing the test statistic to the critical value, what would you conclude? Well, the test statistic was, let's see, from the table, the test statistic was t equals 2.72155. The critical value, that's the one underneath the picture, was, the critical value. The critical value is 2.62449. 2.62449. Well, it looks like our test statistic is going to be in the critical region. So we are going to reject, since 2.72155 is in the critical region. Reject the null since is in the critical region. So, what has been proven in this study? Well, our ending sentence, if we reject the null and our claim is the alternative, our sentence is that there is enough evidence to support the claim. There is enough evidence to support the claim that the average is greater than 40, that the mean is greater than 40.6. Now, since it's greater than 40.6, we can't say that it's less than. So, therefore, it is not at most 40.6. And therefore, the company's claims are false. The company's claims are false. They lie. All right, kids, that's the end of section 8.3. If you guys have any questions, please let me know. And as always, keep calm and keep trucking.